The air you breathe, the water you drink, and the very atoms that make up your body all suggest the same thing. This universe looks like it was built for us. If you change the strength of gravity by just a fraction of a percent, stars would never form. If the expansion of space had been slightly faster after the Big Bang, matter would have flown apart too quickly for a single planet to ever exist. We find ourselves on a world with a perfect atmosphere, protected by a massive moon that stabilizes our tilt, orbiting a sun that provides just the right amount of energy. Everywhere we look, from the microscopic bonds in your DNA to the massive clusters of galaxies, the laws of physics appear to be dialed in with impossible precision. It's as if the universe has a specific set of rules designed to ensure that life isn't just a possibility, but a certainty. This leads to a massive realization. The odds of this happening by pure accident are almost zero. This level of balance raises a massive question about whether the very mechanics of existence were intentionally set to support life. Gravity is the invisible glue that holds everything together, but its strength is set to a terrifyingly specific value. If this force were only slightly stronger, the universe would have collapsed back in on itself, long before the first star had a chance to ignite. Everything would have ended in a big crunch, leaving no room for planets or people. On the other hand, if gravity were just a tiny bit weaker, the clouds of gas and dust left over from the Big Bang would never have pulled together. There would be no suns, no solar systems, and no solid ground to stand on, just a cold, empty void of drifting atoms. This precision is what scientists call fine-tuning. Think of the universe like a giant machine with thousands of dials, each one controlling a fundamental law of nature. If you move the gravity dial by the width of a hair, the machine breaks. This balance allows stars to live for billions of years, providing the steady heat necessary for life to evolve on a nearby planet. Without this exact setting, the chemical elements like carbon and oxygen that make up your body would never have been forged inside the hearts of dying stars. The way gravity works across the entire cosmos is also remarkably consistent. Whether you are looking at a falling apple on Earth or two galaxies colliding millions of light years away, the math remains the same. This consistency allows the universe to be predictable and stable. This stability is the only reason complex structures like trees, mountains, and human brains can exist without being ripped apart or crushed. Does it make sense that a random explosion like the Big Bang resulted in such a perfectly calibrated force? When you look at the sheer scale of the universe, it seems impossible that gravity landed on the exact number required for us to be here. This force isn't just a random occurrence. It acts as a foundation that supports every other law of physics. It creates the pressure needed for nuclear fusion and the orbits that keep our planet at a safe distance from the sun. Everything we see is resting on this one specific value that seems almost suspiciously perfect for our survival. This leads us to look even closer at the very particles that build our world. Gravity provides the structure, but the materials used to build the universe are just as precise. At the most basic level, everything you see, the trees outside, the water in the ocean, and the air in your lungs, is made of atoms. These atoms are held together by the electromagnetic force, which acts like a microscopic magnet. If this force was slightly different, atoms would either fly apart or stick together so tightly that chemical reactions would be impossible. You wouldn't have water molecules, and you certainly wouldn't have the complex chains of DNA that tell your body how to grow. Consider the simple miracle of a drop of water. It requires 2 hydrogen atoms and 1 oxygen atom to bond in a very specific way. This bond only works because the subatomic particles inside those atoms have the exact masses and charges they do. If the mass of an electron were just a little bit higher, the sun wouldn't be able to shine, and the chemical bonds that hold your cells together would snap. We live in a world where the math of the very small is perfectly synced with the math of the very large. This perfection extends to the elements themselves. Carbon is the backbone of all known life, and it is created deep inside stars through a process that requires a nearly impossible level of luck. Scientists found that the energy levels within carbon atoms are tuned to a specific frequency that allows them to form easily. If that frequency were off by even a tiny amount, the universe would be filled with gas but no solid life. There would be no wood for trees, no calcium for bones, and no iron for blood. Every breath you take is a result of these numbers working in harmony. The oxygen in the air isn't just there by accident. It was produced by generations of stars and then captured by a planet with the right gravity to hold onto an atmosphere. How is it that every single atom in your body follows a set of rules that seem specifically written to allow you to exist? This order isn't just limited to the particles themselves, it's reflected in the very environment we call home. It's easy to think of Earth as a peaceful rock floating in space, but the truth is we are living in a giant cosmic shooting gallery. Space is filled with deadly radiation and high-speed particles from the sun that should, by all rights, strip away our atmosphere and fry everything on the surface. We survive because the Earth has a built-in force field called the magnetosphere. This is generated by a massive ball of liquid iron spinning deep inside our planet's core. It sounds like something out of a sci-fi movie, a spinning metal engine at the center of the world creating an invisible shield that deflects solar storms. But it is the only reason you aren't being bombarded by radiation right now. To put this simply, think of the Earth like a house in the middle of a blizzard. The magnetosphere is the sturdy roof and insulated walls that keep the storm outside so you can sit by the fireplace in peace. Without that spinning iron core, we would end up like Mars, a dry, frozen desert with no air to breathe. This leads us to the first major idea, the rare Earth hypothesis. This suggests that while there might be billions of planets out there, the odds of one having a perfect iron core, a massive moon to keep it stable, and the right chemical balance are so low that Earth might be a 1 in a trillion miracle. This ties directly into the anthropic principle, which we touched on earlier. Essentially, this theory argues that we shouldn't be surprised the universe is so perfect, because if it weren't, we wouldn't be here to notice it. It's like a fish marveling at how perfectly the water fits its fins. The environment had to be exactly like this for the observer to show up in the first place. But even if we accept that we are the lucky observers, the level of detail is staggering. The water we drink didn't just appear, it was likely delivered by icy comets during the Earth's violent youth. Even the way water expands when it freezes is a glitch in physics that saves life. Most liquids shrink when they freeze, but ice floats. If ice sank, oceans would freeze from the bottom up, killing all marine life and turning Earth into a solid ball of ice. Instead, the ice creates a blanket on top, keeping the liquid water underneath warm enough for life to survive. This hidden order in the environment makes you wonder if the stage was set long before we arrived. The precision of the universe has led scientists to explore a broader idea. What if this is just one version among many? In modern physics, this concept is often described as the multiverse. It suggests that our universe might be one of countless others, each with its own set of physical laws and constants. In this framework, the balance observed in our universe does not need to be unique. Instead, different universes could exist with slightly different values for gravity, particle masses, or expansion rates. Some of these universes might be too chaotic for structure to form. Others might collapse too quickly or expand too fast for stars and galaxies to ever develop. Out of this vast range of possibilities, only a small fraction would naturally support complexity. This idea connects to what is known as the anthropic principle. It states that the universe must have properties that allow observers to exist, because otherwise there would be no one to notice it. In simple terms, the conditions appear perfect, because only a universe with such conditions can be observed in the first place. This shifts the perspective from rarity to selection. Out of many possible realities, this is one where observation is possible. Some theories in physics, including aspects of string theory, support the possibility of multiple universes by allowing many different solutions for how physical laws can be arranged. These solutions could represent entirely different universes, each operating under its own consistent rules. While this remains theoretical, it provides a mathematical foundation for the idea that reality may be far larger and more varied than what is directly observed. There are also models suggesting that new universes could form continuously, branching off from existing ones or emerging through quantum processes. In such scenarios, the creation of universes becomes a natural outcome of deeper physical laws. Over time, this could result in an enormous number of universes, each exploring different configurations of reality. What makes this idea powerful is how it addresses the fine balance observed earlier. Instead of requiring a single perfectly tuned universe, it allows for many attempts, where only certain outcomes lead to stable, structured systems. This turns the focus away from a single explanation and toward a broader landscape of possibilities. As this perspective expands, it introduces a new layer of thinking. The universe may not be uniquely designed in isolation, but part of a much larger system, where variation itself plays a role. And within that system, the question shifts again, whether these possibilities arise purely from natural processes, or if there is something deeper shaping the entire framework. As science pushes deeper into the structure of reality, it begins to reach a boundary. The laws of physics describe how the universe behaves with incredible accuracy, but they do not fully explain why these laws exist in the first place. This shift moves the discussion from observation to interpretation, where physics meets deeper philosophical ideas. At the smallest scales, reality becomes less intuitive. In quantum mechanics, particles do not behave like solid objects. They exist as probabilities, only taking on definite states when measured. This introduces a level of unpredictability at the foundation of the universe, where outcomes are not always fixed, but described in terms of likelihood. One concept that highlights this is the wave function. It represents all possible states a system can exist in. When an observation is made, this range of possibilities appears to narrow into a single outcome. The exact mechanism behind this transition remains one of the most debated topics in physics, raising questions about the role of observation in shaping reality. Another layer comes from quantum fluctuations. Even in what is considered empty space, tiny amounts of energy constantly appear and disappear. These fluctuations are not random chaos, they follow strict mathematical rules. Some cosmological models suggest that such fluctuations could even play a role in the creation of entire universes, linking the smallest scales to the largest structures. Beyond quantum physics, there are efforts to unify all known forces into a single framework. The search for a theory of everything aims to connect gravity, electromagnetism, and nuclear forces under one set of principles. While progress continues, a complete theory has not yet been confirmed. This leaves open the possibility that the current understanding of physics is only part of a much larger picture. What becomes clear is that the deeper science goes, the more it reveals both answers and limits. The universe can be measured, modeled, and predicted to an extraordinary degree, yet its foundation still holds unanswered aspects. The rules exist, the balance is precise, and the origin follows a defined path. But the reason behind these layers remains open to interpretation. This point marks a transition from what can be tested to what can be considered. The universe presents a structure that is consistent and deeply ordered, yet not fully explained at its core. And that leaves one final step, bringing all these ideas together into a single clear perspective. Thanks for watching, and I'll see you in the next one.